In empty space, two charged particles push and pull against each other with measurable force. We observe them violently snapping together or repelling apart. Observing this physical push and pull is straightforward. Quantifying the exact mechanics of that motion is a significant scientific challenge. For early physicists, the central challenge of electrostatics was finding a way to translate the physical reality of three-dimensional space into predictable mathematical proportionalities. The framework that solved this mapping problem is Coulomb's law. Coulomb's law is a deterministic bridge built on three strict physical pillars: charge magnitude, spatial separation, and environmental permittivity. To construct this equation, we require an absolute physical baseline. Imagine a pure vacuum containing nothing but two isolated point charges suspended in space. This diagram models our baseline scenario. It is driven by the individual magnitudes of isolated charges Q1 and Q2. The resisting variable is the empty space, measured as linear distance separating their centers. Their interaction dictates pure attraction or repulsion along a straight vector. We have mapped the system's geometry. The structural tension moving forward is determining how we translate this layout into an exact calculated force value. We begin the calculation with our first physical pillar, charge magnitude. Look at this first proportionality equation. It dictates that the electrostatic force scales directly with the mathematical product of the two interacting charges. Next, we factor in our second physical pillar, spatial separation. This second equation outlines an inverse square relationship. The force dissipates geometrically as the distance between charges grows. These two rules oppose each other. The magnitude of the charges drives the force up, while the increasing distance aggressively bleeds that force away into the surrounding space. We have defined the behavioral rules of the particles, but a proportional relationship merely outlines a trend. It is not yet a calculable equation. To find an exact value, we must combine these two independent conditions into a single, unified mathematical statement. In physical space, these factors interact simultaneously. The force factor shrinks against the x-axis due to distance, while scaling up on the y-axis based on the charge multipliers. Returning to the source text, we see the resulting merged expression. But a fluid proportionality symbol is not an equal sign. Converting it into rigid arithmetic requires inserting a constant to balance the scales. This introduces our specific balancing agent, the electrostatic force constant, denoted mathematically as K. While this finalizes the structure of the equation, the newly introduced K is currently a placeholder for the electrical properties of the environment. It is a mistake in introductory physics to treat K as arbitrary mathematical filler or as a universal constant like gravity. Look at this highlighted note. The value of K is completely captive to the physical environment where the charged particles are currently interacting. A physical medium, like water, humid air, or glass, acts as a dampener. It physically interferes with and degrades the electrostatic force field. To calculate the pure, unadulterated force, we must bypass this interference. We have to assume a medium with zero standard physical resistance. We define this baseline medium as a pure vacuum, or free space. To complete our mathematical model, we cannot ignore the medium. We must explicitly quantify the specific electrical properties of a total vacuum. When the separating medium is a pure vacuum, empirical testing yields a massive value for K. Using that flat number hides the structural geometry of the force. For advanced physics, we require a breakdown into a more complex formula. Look at the 4π component in the denominator. This accounts for the spherical, three-dimensional geometry of the force, which radiates outward from a point charge in all directions simultaneously. That brings us to the core concept of the formula, epsilon naught, the absolute electrical permittivity of free space. Epsilon naught has an exact numeric value. It defines the specific, inherent resistance of a pure vacuum to an electric field. Discovering epsilon naught proves that a pure vacuum possesses measurable physical properties that dictate the strict speed limits of electrostatic force. We have defined charge magnitude, derived the spatial geometry, and quantified the properties of a vacuum. We can now assemble the master synthesis. This is the formalized version of Coulomb's law. The numerator represents the driving force created by the two charge magnitudes. The spatial divisor accounts for geometric dissipation over distance. Finally, the constant block establishes the inherent electrical resistance of the three-dimensional spherical environment. We began by observing two charges pushing against each other. By mapping that behavior, we achieved a rigorous, heavily parametrized mathematical model. This structurally unpacked formulation allows physicists to execute completely deterministic calculations of unseen forces operating in empty space. While this isolates a pure vacuum baseline, introducing any real-world medium into a system, like water or glass, simply requires modifying the epsilon naught value inside this fundamental blueprint. Every subsequent rule of electrodynamics relies on the structural integrity of this single equation. Coulomb's law stands as our ultimate mathematical blueprint for understanding exactly how the building blocks of the universe interact across the void.